Okay, so I'm going to give people a few minutes to gather here. Hopefully, we'll get more than two, although, if there is two and we have questions, we can definitely work on some stuff. I'm planning kind of a general overview of everything that we've done. We'll definitely talk about enzymes. We'll definitely talk about acids and bases. I printed out some pretty pictures that we can use to talk about the different types of biomolecules. And all of this is meant to get us ready for the biochem test on Wednesday for 2B and 4B and Thursday for 2A. I'm gonna be really happy once we get back to normal with this schedule. It's been kind of hard to keep up with things. So I think probably if you've done this before, you know how this works. But if you're not familiar, I'm sitting here in my office at my house, which, as you can see, we need to decorate. There's nothing hanging up. My wife just shopped for a bunch of frames today, so hopefully we'll get some stuff. And if you and I kind of let you guide this. So if you have any questions, go ahead and hit me up in the chat box on the side. I'm also gonna have my email open. So if you would prefer to send me a question via email, you can do that as well. And we will kind of let you guide this, and then if we get a few other people in, um, we can kind of do a good general review of everything. Um, it's been a little hard to get any consistency, but we're going to do the best we can. So um, I'm gonna give like 2 minutes for other people to show up. If you do have a question in the meantime, don't hesitate to type it in that chat area over there, and then we'll get this party started. So I'll be right back. Okay, so still just the two of you. So we may as well go ahead and get started with kind of a general overview. Let me just see if I can signal boost this on Twitter right now. Feel free to tell your friends that this is happening. Um, and we'll take it from there. All right. So um, the two of you are in for a treat because I'm about to kind of go through most of what we need to know for the test. My tests all end up pretty similar. It's going to be a mixture of probably some matching, probably some multiple choice, and definitely some short answer. For this one, we'll be focusing more on polarity, on the idea of polarity, that water is a polar molecule, and therefore things that dissolve in water are also polar. Things that don't are obviously nonpolar. And we'll also need to know a little bit about acids and bases and how we deal with that from kind of a homeostatic standpoint. And you may also need to know information about the various types of biomolecules. Speaking of which, I've taken the liberty of printing out some pictures. Really went all out for this live stream. So this, as you can sort of see at the top of the page, it's a little bit cut off because I enlarged it. This is glucose. Glucose is a monosaccharide. You may remember that that is the monomer of a carbohydrate. Um, one of these is called a monosaccharide, a single sugar. If you put two of these together, you create a disaccharide, which is two single sugars bonded together covalently. And if you put many of them together, you get a polysaccharide. Examples of disaccharides would be lactose. Maltose is actually two glucose molecules together. Sucrose, the kind of sugar you get in 5-pound bags at the supermarket, is also a disaccharide. And monosaccharides and disaccharides are both used for kind of quick energy. When you need energy right away, monosaccharides and disaccharides are your best energy source. Then, so this, as you can see, if you do the quick math and if you just kind of know what carbohydrates are, um, this has the formula C6H12O6, and the ratio of carbon to hydrogen to oxygen in a carbohydrate is generally 1 to 2 to 1. So you've got basically twice as much hydrogen as you do anything else. So that is a monosaccharide, the building block of a carbohydrate. This right here, and I printed off two pictures for this one. I'm not sure you'll be able to see the second very well, but we'll try. This is an amino acid. You can see here some of the features here. This is the amino group that's outlined in red here. That's how amino acids get their name. And that's also where we find nitrogen. Proteins are unique among the molecules that we've studied in that they contain nitrogen. So most of the urea that you pee out, that you excrete through your urine, is made up of sort of worn out amino acids that have been processed into another form. You also have the carboxyl group. They call it a carboxylic acid here. And then you've got this single hydrogen atom and then the R group. You'll remember that there are 20 different amino acids, and so there are 20 different R groups. The R group is the only place where these amino acids differ. And the properties of those R groups can often determine whether the protein as a whole is polar or nonpolar, and then what it will do in terms of transport, in terms of getting across the cell membrane, etc. Now, I wanted to also highlight this right here is the way that two amino acids come together to form a protein. Eventually, they would form a protein. This is a peptide bond. You see here the carboxyl group of one amino acid and the amino group of another. You lose a hydrogen from one side, an oxygen and a hydrogen from the other. You may remember that those elements together make water. And what you get in the end in a dehydration synthesis reaction is you form a bond that is called a peptide bond when we deal with amino acids forming proteins specifically, and a molecule of water right there. So dehydration synthesis, again, is the formation of a bond with the loss of water. The opposite of this, so if we were to break this peptide bond to form amino acids, we would be performing a hydrolysis reaction. Hydro meaning water, lysis referring to the breaking of bonds. So that's proteins. Now, this one right here is one of my favorites. This is what we call a triglyceride. This is what most of the fats that you would have in your diet would look like. Other examples of lipids would be cholesterol. Certain steroid hormones are lipids as well, which means they don't dissolve in water, which means they have to get through your bloodstream some other way. And so we see here that on this side, the sort of, I think that's sort of a bluish green color there, you see glycerol, and that is an alcohol. That is one of the building blocks of a lipid. And then those long chains of carbon and hydrogen, which we still have one of in class, are fatty acids. Fatty acids, really, all they are just big long chains of carbon and hydrogen. You see up here that all these that have all single bonds are saturated with hydrogen. That means they have as many as they can get. And these are called saturated fatty acids. This down here is an unsaturated fatty acid because it has one double bond. You've taken out some hydrogen, so it doesn't have all of them that could bond to it, and there's a double bond there instead. So, if something is entirely unsaturated, it's usually going to be liquid at room temperature. It's usually going to come from plant sources. So your olive oils, your peanut oils, things like that would be unsaturated. And your animal fats, so butter, milk, meat, all of those, the fat from those would tend to be saturated. They tend to pack together more tightly. They tend to be solids at room temperature, and so they're often a little harder to break down. Most people will recommend a diet that if you that is relatively low in fat, and of that fat, they recommend that most of it would be unsaturated fat, or yeah, unsaturated fat. Um, Remember, fat is really important because it provides insulation. It can be a backup energy source if you run out of carbohydrates. Endurance runners really focus on that. You may not know that Mrs. Bork, my esteemed colleague, actually just ran the New York Marathon in just over 4 hours. She's real fast, and her ability to train through that wall to suddenly start using fat as fuel instead of carbohydrates really was key for her running the second half of the marathon just about as fast as the first. She actually, like, her splits were kind of perfect. I'm kind of jealous. And so she was able to manage that really well by being able to use the fat inside her fat cells as fuel. Um, so that is kind of a brief summary of all of the biomolecules. When we talk about the uses of these, when we talk about energy, carbohydrates are always our preferential source. They're easy to break down. They require relatively little oxygen, and they do give us um, sort of the most bang for our buck. There are so trying to trying to remember what I was. Yeah, so gram for gram. Um, there are 4 calories that can be provided. This is where I was going with this. Sorry. Um, there are 4 calories that we get from every gram of carbohydrate that we burn. Um, Remember, calories are a unit of energy. So if something has calories, it will provide you with energy, usually in the form of carbohydrates. Any food material would have some amount of calories. And if you needed to, you could break down almost anything. Carbohydrates are always going to be first. First, it's going to be your monosaccharides and your disaccharides, your smaller sugars with quick energy. Then your body is going to start to break down glycogen. Glycogen is the storage form of carbohydrates, your polysaccharides that you store up in your muscles and in your liver. And then, and only then, will you start to break down fat. So a lot of people who are trying to burn fat, they recommend that you stay in a certain heart rate zone that's conducive to fat burning, and b that you work out for a very long time, because eventually you're going to start losing those carbohydrates, and then you'll need to depend on fat for fuel. Fat, gram for gram, contains 9 calories per gram that you burn. However, since it requires so much more oxygen, and since we have to breathe harder and potentially produce more carbon dioxide in our blood as a result, we tend to shy away from that. We try not to use lipids as a source of energy. Now, when it comes to proteins, proteins do so many important things. They're structural compounds. Collagen is a really important one that we've talked about quite a bit. They form our hair, our skin, our nails, our joints. They make our bones and muscles strong. They're really important for tissue repair of all kinds. And of course, there are enzymes that are catalysts. They speed up chemical reactions in our cells by reducing their activation energy. And so, for all those reasons, we want to use proteins for their specific special jobs, and we want to avoid using them for energy if at all possible. We sort of joke, but it's not a joking matter at all. In severe cases of famine, when there are droughts, when there are food shortages in usually in other parts of the world. Thankfully, we don't often have to deal with it here. But when there is famine, often that's when we see that proteins start to get broken down. The proteins that, so for instance, if you look at, when I was living in Africa, a lot of kids were malnourished and they particularly didn't get enough protein in their diet. And so you would notice that their stomachs would get sort of distended. Like you'd see a kid that clearly hadn't eaten very much in a long time who had a big belly, and you would think that they were eating well. Like we see chubby kids in the US all the time because we're lazy, we play too many video games and we don't get outside enough. But in this case, the smooth muscle that keeps the stomach sort of in place, and the abdominal muscles that sort of maintain structure here in the middle of our body, they were starting to break down because they needed that protein for energy. And so, generally, when you see that, that's not a good sign at all. It's a sign that they're, potentially very sick and don't have those really ready energy sources. So, that was a bit of an aside, but that is kind of a summary of all the biomolecules in general. Um, you guys are very quiet tonight. There are only four of you, but if you do have questions related to anything that we just talked about for the last 10, 12 minutes or so, feel free to hit me up in the chat, or go ahead and put something on my email. I've got that open now as well. And after I take a sip of water, we'll talk acids and bases. By the way, if you want some good music to listen to while you're listening to me, I wouldn't want you to distract yourself, but it's a band called Guster that I really like. They've been around for like 25 years now. Real good guys. Went to Tufts University in Massachusetts. I highly recommend them. Check them out when you get a chance. Lots of stuff on YouTube related to Guster. So anyway, I'm gonna jot down a few things that I think will kind of simplify pH for you. Um, at least I didn't share the Kahoot, so let me take a moment here, and I am gonna go ahead. Actually, you know what? I'm gonna write a great big note because I don't want to interrupt the flow of the live stream here, and I am going to share the Kahoot later on. See, thank you for holding me accountable. I had just forgotten to do that. Or had I? Wait a minute. Let's see. I think I might have. Oh yeah. Mhm. I sent an email on Friday at 2:48 p.m. that actually had the Kahoot already shared. I wasn't sure if I had done that or not. I've been very, very busy. But yeah, if you go back to that email from Friday, the Kahoot is in there, and you can play as often as you want. So, what am I thinking here? Yes, pH. So let's talk about the lungs. So if the lungs can control pH by altering the concentration of carbon dioxide. Carbon dioxide, as we've talked about, forms an acid when it dissolves in water. The technical name of the acid is carbonic acid. But the important thing to know is that the more CO2 that is dissolved in our bloodstream, that is, the more we can't get rid of, the lower the pH of our blood will be. Ideally, blood pH should be between 7.35 and 7.45. That is slightly alkaline or basic, but from time to time, we need to alter that concentration for any number of reasons, or we need to respond to a change in pH. And the lungs are one of the things that can do that. The lungs actually do it the quickest. It takes a lot longer for the kidneys to take care of these things because CO2 has a pretty profound effect and it's easy to get rid of a lot really quickly. So, if we were to increase the concentration of carbon dioxide, the pH would go down. The more carbon dioxide we have in the blood, the more acidic that blood will be. And so the way we simulated that was by rebreathing. That is, when you breathe into a paper bag, you are doing exactly that. You're rebreathing your own exhaled air. That exhaled air, of course, would have a higher concentration of CO2. You wouldn't be bringing in as much oxygen from around because you're in this enclosed space, and therefore you're not going to lose as much CO2 and your pH will go down. Now, another way to do that, if you were to want to get rid of, or if you were want to retain more carbon dioxide, you could exhibit what's called hypoventilation, where you slow your breathing rate down and you don't exchange as much gas with each breath. Generally speaking, you expel about 3/4 of a liter of CO2 with each exhale, and you bring in about 3/4 of a liter of oxygen with every inhale. Um, if you were to breathe more shallowly, I think that's a word. You wouldn't. You would bring in. You would get rid of less CO2 and therefore keep the pH down. Now, the one that we're more familiar with is hyperventilation. It is a response often associated with anxiety, but there's also a really important homeostatic component to it because what hyperventilation does by increasing the rate of breathing and the volume of breathing, often by 4 times what it normally is, you're going to bring the CO2 concentration way down, which is going to bring the pH way up. You saw that very quickly in the simulation that we did. The pH went up to about 7.6, 7.7. Now, if your pH was lower before, that would actually be a really quick way to bring your pH back up to where it needed to be. Um, so that's what happens in the lungs. The kidneys get a little more complicated, but not much. So I'm going to kind of summarize this as well as I can. So, let's say you wanted to increase the pH. You could make sure you had a low concentration of hydrogen in the blood. Technically, pH is a measure of the concentration of hydrogen ions in a solution. So, the more hydrogen you have, the lower the pH will be. If you're getting rid of a lot of it in the urine, and therefore you don't have a lot in the blood, then the pH will increase because you're getting rid of the thing that makes that blood acidic, or one of the things that makes that blood acidic. The other thing you could do if you wanted to increase the pH is you could retain a lot of here. Um, The other one is bicarbonate. You may remember HCO3 was the formula for the bicarbonate ion. Now you see why I want people to take chemistry. Um, but if you do that, so if you retain most of the bicarbonate, you have the same effect. So you could do both. You could get rid of as much hydrogen as possible, which would keep it from making the blood acidic. And you could retain as much bicarbonate as possible. And bicarbonate is the same ion you would find in baking soda, which is definitely a base. We use it to neutralize vinegar all the time. Um, and if you had these conditions, you would increase the pH even quicker. Now, I don't think I really need to write it down, but if the opposite were true, if we wanted to decrease the pH, we would want to keep more hydrogen because the higher the hydrogen concentration, the lower the pH. And we would want to get rid of as much bicarbonate as possible because the more bicarbonate we have, the higher the pH will be. So that would result, if we were to examine the urine, we would find a lot of bicarbonate because we're getting rid of it. And we wouldn't find a lot of hydrogen at all because we're trying to keep as much as we can to get that pH back down. So if you can understand how the lungs and the kidneys work together to control pH, you're going to be golden. That's probably the trickiest thing that we have on this test. There's a lot to it, but I think that the acid base stuff is where it gets trickiest. If you do have any questions coming in before you sit down and take the test these next couple days, then I'm happy to help out. Okay, so acids bases. I'm going to give you guys a minute to kind of wrap your heads around this. Make sure that if you have any questions, don't hesitate to hit me up. I mean, I'm happy to have a conversation back and forth with Elise here, but if the rest of you guys want to pitch in, I'm more than happy to help. So, another sip of water, and then I'm thinking we talk enzymes. Okay, so 3 big things about enzymes. So, the first thing, they're specific. So, we used a lock and key to explain the action of enzymes and the specificity of enzymes. Specificity was incidentally always a word that my AP Bio teacher could not say. He's actually the reason I'm a teacher. He was an inspiration in so many ways, but not in terms of his pronunciation of specificity. He always used to say like specificity or something like that, but he got his point across. We knew what we meant. We knew what he meant. So the first thing to know is that they are specific. One enzyme to one substrate. Lactase is the example we always use in class. Lactase is the enzyme you can't make if you're lactose intolerant. Lactase acts on lactose. That's it. It will not bind to any other substance at all. Even other disaccharides will not bind to lactase. It won't happen because each enzyme has a specific active site. That's the place where the substrate actually binds. And that 3-dimensional shape determines what can bind to that enzyme. And if the enzyme and the substrate can't come together, they can't react. So here's the second thing. I probably should have made this the first thing. I know this is really fascinating viewing with me just staring at a piece of paper and writing. Takes time to draw these pretty pictures, guys. Okay, so um, second thing is they are catalysts, and a catalyst is anything that speeds up a chemical reaction. Could be a lot of different things. Often heat is used as a catalyst. Often reactions are done on like metals, like platinum or manganese or something. We could get into that in chemistry quite a bit, but we're gonna stick to the biochem here. So enzymes are protein catalysts that speed up reactions by whoa, sorry. I hope nobody took a screenshot of that just then because that is a big mistake. So you may notice my mistake here. They speed up reactions by decreasing the activation energy. So the activation energy you can think of as the amount of energy it takes to get a reaction started. The less energy required to start a reaction, the faster that reaction is going to go. So, without an enzyme, you can see that the activation energy is pretty big here. You have to put a lot of energy in to get the reaction started in the first place. That amount of energy really limits the rate of the reaction. You can't make the reaction go as quickly because you have to put so much more energy in it. Here is what happens with the enzyme. It brings the substrate closer together. It reduces the amount of energy to get the reaction started so you can make the reaction go a lot quicker. So, with the enzyme, clearly there's less activation energy, which means the reaction speeds up. So, here's the third thing. So, they are very sensitive to temperature and pH. Remember, enzymes are proteins. Proteins, when they are not at their optimum temperature or pH, they get denatured. When a protein is denatured, and this could be any protein at all, it loses its three-dimensional structure. And we've talked time and time again with proteins about how structure follows function. If that three-dimensional structure, especially for an enzyme, is disrupted in any way, that enzyme can no longer perform its function. So, um, the example that we had in the POGO activity was two different enzymes, an enzyme that was found in humans and an enzyme that was found in bacteria that were found in hot springs. I got to do some great research on hot spring bacteria in Yellowstone National Park. Fascinating stuff. And they live under the weirdest conditions, like super acidic water, um, that's usually somewhere between 70 and 90 degrees Celsius. And they have enzymes that are able to carry out chemical reactions at those high temperatures. You put those enzymes in us, they're useless. They don't work because the optimum temperature for human enzymes to work is roughly 40 degrees Celsius. That's why a low grade fever can actually be beneficial because it speeds up some of those chemical reactions, like the reactions that we use to get rid of viruses and bacteria, because those are chemical reactions just like any other. And they're catalyzed by enzymes, and those enzymes work better at a slightly elevated body temperature. The enzymes that break down food for energy, for example, when we exert ourselves, when we're working out, when we're exercising, our body temperature elevates slightly. And that actually helps us to carry out some of those metabolic reactions to get more energy for our cells. However, a high fever can take that temperature out of the optimum range. Remember, the range was usually somewhere between 35 and 42 degrees Celsius. So about 105 degrees Fahrenheit. Much above that, the enzymes start to denature and they can't do what they do. When enzymes start to go bad, that's when we're in trouble. So temperature is really important. pH is also really important. So salivary amylase is, you may wonder why I'm pointing to my mouth. Salivary amylase is the enzyme in saliva. It breaks down amylose, which is a very specific type of starch. So, anytime we take in starchy foods, breads, pasta, cereal, things like that, that enzyme in our mouth begins to work immediately to start breaking down that carbohydrate because we want to be able to use it as soon as possible for energy. So that enzyme works very well at a pH of about 7 or 8, which is the typical pH in our mouth. Down here in our tummy, we have a pH of about 2, 2.5. And that enzyme will no longer work down there. It'll get denatured. The same thing would happen if you added acid to an egg. The egg white is normally clear. If you add acid to it, it turns white just like you're cooking it. Because all you're doing when you're cooking proteins is you're denaturing them. You're taking them out of their optimum temperature, so they change their three-dimensional structure, and they look and feel and smell and taste different. You're actually performing a chemical change on those substances. And without that three-dimensional structure, they don't do what they did before, and they certainly don't look like they did before. Um, so those are the three take-home messages I wanted to make sure everybody understood about enzymes. A, they're specific, like a lock and a key, one enzyme to one substrate only. They are catalysts. They speed up chemical reactions by decreasing activation energy, and they're sensitive to temperature and pH. If they get out of their optimum range, there can be very serious consequences because as they lose their three-dimensional structure, they start to lose their function as well. Okay, so one last sip of water, and then we'll talk about water. And I think we'll probably call it a night unless anybody has any other questions. So feel free, like I said, to chime in over there. And I am happy to help you in any way I can. Okay, so water. Um, Water makes up 60 to 80% of our body. It makes up a good amount of our cells. So, really important that we understand its properties. It's a polar molecule, which means that it has. Um, Actually, let me talk about Elisa's question before we move on. If you denature a substrate, can it ever turn back to its original shape? Um, in some cases, yes, but generally speaking, denaturation, the process of sort of disrupting the three-dimensional structure of a protein, particularly an enzyme. Now, we're not talking about denaturing a substrate. The substrate is the molecule that the enzyme acts on. When we're talking about denaturing something in this process, we're talking about denaturing the enzyme. And generally speaking, it doesn't return back to its original shape. If there are sort of short term changes in temperature or pH, it may be slightly reversible, but usually it's not. So I think for our purposes, let's assume that when we denature an enzyme, we can't return it to its original shape. I think we can go with that moving forward. So back to water. So water is polar. That means that it has partial positive and negative charges. That means that anything else that has those partial positive and negative charges, any other polar molecules like glucose, or any ionic compounds like salt or something like that, can also interact with water and can dissolve in it. That comes in really handy for water soluble vitamins that are really easy to get through the bloodstream. That comes in really handy for substances that need to go from one place to another very quickly. Because the bloodstream obviously is made of mostly water. Anything that can dissolve in that water tends to move through really easily. The problem with those polar substances comes when you get to the cell membrane. Cell membrane, as you remember, is composed of a lipid bilayer. We went over this in class the other day. That lipid bilayer is polar on the outside because we have to be able to interact with water wherever we go because cells are in water, and non-polar on the inside. So things that are polar, especially if they're a little larger, often have trouble passing through the cell membrane because they are polar and most of the membrane is non-polar. So a lot of them need transport proteins to get through the cell membrane properly. It's usually not a problem. It usually doesn't require energy, but it does require help from some sort of transport protein to get them through. Um, so water, as I said, dissolves just about anything. That means that ionic compounds can serve as electrolytes and conduct electricity in solution. Sodium is a great example of an electrolyte. Potassium, calcium, all of those have really important functions in nerves and muscles and other cells. Water also has a very high heat capacity or specific heat capacity. Some of you are learning about that in chemistry right now, and that measures the amount of energy it takes to raise or lower the temperature of something. Water happens to have a very high specific heat capacity, which means that it takes a lot of energy to heat it up or cool it down. That makes it really easy to control the temperature of the watery environment that we happen to live in. Water also has a very high heat of vaporization, which is the amount of heat required to turn something from a liquid into a gas. And for that reason, sweat is a really efficient cooling mechanism because you're taking heat from the body. And because it's water, you're taking a lot of heat from the body. So, more so than if you were to evaporate other things, you're removing quite a good amount of heat from the body when you perform that function, when you evaporate liquid sweat from the surface of your skin. Liquid sweat, great band name. Then water also takes part in chemical reactions. Dehydration synthesis is when you lose a water molecule and form a bond. That's how monomers form polymers. And hydrolysis is how polymers are broken down into their monomers when water is added and bonds are broken. It's very important that you understand the difference between those two things. I think it's a pretty easy distinction once you get used to it. Then water also has cushioning ability. Water is it is the most important inorganic compound in the body. You may remember that we form a distinction between organic compounds, which are compounds that contain carbon, and inorganic compounds that don't. So most of your salts, um, a lot of acids and bases don't have carbon. Um, so they're considered to be inorganic compounds. Your organic compounds are things like carbohydrates and proteins and lipids, and also nucleic acids, although we won't cover that on this test. Um, I think I'm not sure what else there is. I think we might have covered all the bases. So, Elise, if you're still here, if you have any questions, I'm happy to field any other questions that you might have. Otherwise, I got to get up early to vote tomorrow, and we'll probably wrap this up. So, will this test be similar to the quiz we took a few weeks ago? In a lot of ways. Since then, we've added a bit about enzymes. We've added a bit about the properties of water, a lot more with acids and bases. But in terms of the content based on the basic macromolecules, your carbohydrates, your proteins, your lipids, it's going to be pretty similar. You got to know the same stuff. I might present it in a slightly different way, but the content doesn't really change. So if I were you, I would take time to look at the study guide. Certainly, some of that is a little more difficult than what you're going to have on the test, but I would rather you prepare for something a bit more difficult and then find the test easy than the other way around. So that's definitely worth taking some time. If there are things that are looking weird there, I'm happy to answer any questions that you have when you come in. Um, I would also take some time with the notes. The notes are pretty comprehensive and cover pretty much everything that you need to know. The biochem homework that went along with that would be a good thing to look at again. I know it's been a while, but it's worth another look. Um, and really, I think that's about it. I think if you put in the time over the next couple days, this is going to be tough. For a lot of people, it's the toughest test of the year, but it's doable if you put the work in. So, um, hopefully, I've given you a lot of different tools, a lot of good information to work with, and the rest is up to you. So, good luck studying. Hopefully, you'll be able to study enough so that you'll be able to carve out some time to go see the boys' soccer team tomorrow. I know I'll be there. That's the reason we're doing this tonight instead of tomorrow. Sorry for those of you who were thrown off by that, but hopefully, you're watching it archived and you still get a lot out of it. So, hope this was helpful. And I think I'm going to go ahead and sign off and get to bed. Have a great night.